AI winters refer to periods when enthusiasm, funding, and institutional support for artificial intelligence declined sharply. These downturns followed waves of optimism that exceeded what technology could realistically deliver. Understanding AI winters helps explain why progress in AI has unfolded in cycles rather than along a smooth, linear path. The history of artificial intelligence is not a steady upward trajectory. Instead, it consists of repeated cycles of excitement, disappointment, and renewal. Each cycle reflects a gap between expectations and reality. AI winters emerged when promises outpaced practical results and confidence eroded. An AI winter is defined as a sustained period during which investment, research funding, and public interest in AI decline significantly. These periods are not caused by a lack of ideas, but by unmet expectations and a loss of institutional trust in AI's near-term potential. The term AI winter draws an analogy to economic winters, where activity slows and resources contract. In AI, winters occur when optimism freezes, projects are cancelled, and research becomes harder to sustain. The metaphor highlights both severity and temporary nature. Early AI researchers made ambitious claims. They predicted human-level intelligence within decades, and sometimes within years. These claims were often sincere, but underestimated the complexity of intelligence and overestimated available computing power, data, and algorithmic maturity. The gap between vision and reality became increasingly apparent. Early systems worked in constrained settings but failed in real-world environments. As limitations surfaced, confidence declined, especially among funding agencies and policymakers who expected broader impact. The first major AI winter occurred in the 1970s. After early enthusiasm in the 1950s and 1960s, progress slowed. Governments reduced funding when promised breakthroughs did not materialize, particularly in areas like language understanding and general reasoning. Funding cuts played a central role. AI research relied heavily on government support, and when confidence waned, budgets were redirected. Without stable funding, many research programs were scaled back or abandoned entirely. Technical limitations were significant. Computers were slow, memory was expensive, and datasets were small. These constraints severely limited what AI systems could do, regardless of how clever the underlying ideas were. Symbolic AI systems depended on explicit rules and logic. While effective for structured problems, they struggled with ambiguity, noise, and real-world complexity. These weaknesses became increasingly visible as systems were tested beyond laboratory settings. A second AI winter occurred in the late 1980s and early 1990s. This period followed the rise of expert systems, which had initially appeared commercially promising, but ultimately proved difficult to scale and maintain. Expert systems required constant manual updates. As rules accumulated, systems became brittle and expensive to maintain. Organizations found that promised efficiency gains were offset by high operational costs. Commercial disappointment accelerated the downturn. Many companies invested heavily in AI products that failed to deliver expected returns. As a result, AI became associated with risk rather than opportunity. A major issue was overgeneralization. Narrow systems designed for specific tasks were marketed as broadly intelligent. When these systems failed outside their narrow domains, trust collapsed. Loss of trust was not limited to investors. Governments, corporations, and academic institutions grew skeptical. AI shifted from being seen as transformative to being viewed as unreliable and overhyped. Expectations played a decisive role. When timelines are unrealistic, even genuine progress can feel like failure. AI winters illustrate how managing expectations is as important as technical advancement. Media coverage amplified the problem. Sensational headlines created inflated expectations among the public and decision makers. When reality failed to match these narratives, backlash followed. Evaluation methods were also immature. Many systems lacked rigorous benchmarks, making it hard to assess real progress objectively. This made it easier for weak systems to be oversold. AI research ecosystems were fragile. Heavy dependence on short-term funding made them vulnerable to shifts in political and economic priorities. When funding dried up, entire research areas stalled. Tension existed between academic goals and industry expectations. Researchers explored long-term questions, while funders wanted immediate applications. This mismatch intensified disappointment. AI winters revealed fundamental truths about intelligence. Human cognition involves context, learning, embodiment, and adaptation, qualities far harder to engineer than early researchers anticipated. One key lesson was that intelligence is not monolithic. Narrow competence does not equal general intelligence. Confusing the two contributed heavily to unrealistic projections. Another lesson involved data. Early AI lacked sufficient data to learn from experience. Without large, diverse datasets, systems could not generalize effectively. Compute limitations also mattered. Many algorithms that work today were theoretically known decades ago, but were impractical without modern hardware. Compute limitations also mattered. Many algorithms that work today were theoretically known decades ago, but were impractical without modern hardware. Machine learning represented a shift from hand-coded rules to data-driven learning. This transition addressed many scalability problems that symbolic systems could not solve. Statistical thinking allowed systems to handle uncertainty more naturally. Probabilistic models replaced brittle logic, improving robustness in real-world settings. Infrastructure improvements were critical. The rise of the internet, digital storage, and distributed computing changed what was feasible for AI research and deployment. Infrastructure improvements were critical. The rise of the internet, digital storage, and distributed computing changed what was feasible for AI research and deployment. Commercial alignment also improved. AI began solving clearly defined problems with measurable value, such as search, recommendation, and pattern recognition. Today's AI boom rests on stronger foundations. Data abundance, scalable compute, and algorithmic maturity reduce, but do not eliminate, the risk of another winter. However, hype has not disappeared. Overclaims still occur, especially around general intelligence and autonomy. Awareness of AI winters helps contextualize these narratives. Avoiding another AI winter requires responsible communication. Claims must align with evidence, and limitations must be acknowledged openly. Governance plays a role. Stable funding, long-term research support, and realistic policy expectations help prevent boom and bust cycles. Research discipline matters. Clear benchmarks, transparent evaluation, and peer review reduce the risk of inflated claims dominating public discourse. AI winters should not be seen as failures, but as corrections. They reset expectations and redirect effort toward more sustainable paths. Historical awareness is valuable. Understanding past cycles helps researchers, investors, and policymakers avoid repeating the same mistakes. The key takeaway is balance. Progress requires ambition, but also humility. AI advances when claims are grounded and development is incremental. For policymakers, AI winters highlight the importance of stable, long-term investment rather than reactionary funding decisions. For practitioners, the lesson is honesty. Deploy systems for what they can reliably do, not what marketing suggests they might do someday. For the public, AI literacy helps distinguish real capability from speculation. Informed skepticism supports healthier technological adoption. AI winters remind us that progress is uneven. Breakthroughs often, each winter contributed knowledge. Failures clarified limits, refined methods, and shaped future research directions. Rather than erasing value, winters filtered unrealistic approaches. Understanding AI winters encourages patience. Complex systems require time, iteration, and learning from mistakes. Modern AI benefits from these lessons. Today's systems are evaluated more rigorously and deployed more cautiously. Still, vigilance is necessary. The same forces that caused past winters, hype, overpromise, misalignment, can reappear. History does not repeat exactly, but it often rhymes. Awareness helps guide responsible innovation. AI winters show that setbacks are part of progress. What matters is how systems, institutions, and societies learn from them. Next, we move from historical cycles to modern machine learning, examining how data-driven approaches transform AI and why today's systems differ fundamentally from those of the past.